Introduction to Statistical Learning. We're in Chapter 4, and we're on the last question in Chapter 4. We're on question 16, which is part of the applied problems. I am doing this video in R. It's also possible to do it in Python. Anyway, so here we are going to use a data set that comes in the ISLR2 package, and it's called the Boston data set. And we're going to fit different classification models in order to predict whether a given census tract has a crime rate above or below the median. Okay? And so we're supposed to explore logistic regression, LDA, naive Bayes, k-nearest neighbors, etc., etc. Okay. So this is basically just a repeat from question 14, but 14 was using the auto data set. Okay. And so I don't think that I'll give a whole lot of explanation here. I will just kind of walk through some of the code, but the code really is just copied and pasted from question 14 with the modifications necessary for this data set. So we're just going to load the ISLR2 package and install and load it. And then we're going to bring up our data set, which is Boston. Okay, and I'm just calling it D just to reduce typing. And so now I need to define my my outcome variable, which is above or below the median crime rate. So I have this variable that I'm creating called med crime, or median crime. Okay, and so I just find the median of the crime variable within our data set. All right, and then I'm going to attach or append to our existing data set, D, or Boston, a variable called mcrim for median crime, which basically says if the crime variable in data is greater than the median, which I've already defined, give it a 1, otherwise give it a 0. Okay. So now, with that, so now I have a data set that has the median crime, above or below the median crime. Okay. And so now I need to generate I need to create a data frame on which we're going to do our classification. Okay. So I'm calling this D2, and for D2, I'm just simply eliminating the first, I'm eliminating the crime or the crim variable. In fact, let me show you what D looks like. Okay. So D has this crime variable, okay, and we are predicting M crime, okay. Well, if I'm going to predict M crime, because I've defined it by crime, I probably don't want to use crime to predict M crime, right? It's kind of a tautology. So I'm defining a new data set here called D2, which I'm just eliminating that first variable, which is crime, okay. Now I need to break my data now into training and testing sets. And so I'm going to use 75% of the data as training and the rest is test data. Okay. So I'm defining a proportion of my data that's going to be used for training. Okay. 75%. And then I find out how many observations that is by multiplying that proposition or that proportion by the number of rows in D, and I'm rounding up. Okay, and then I'm going to train in numbers from 1 through the number of observations I have in my data set. So I'm going to randomly sample 75% of my data to be training data. Okay, and so now I have my training set, which is D2 train, which is just simply D2, and I'm indexing the randomly sampled observations, and then D-test is just the rest, right? So just the observations in D2 that are not part of the training index. Okay. Okay. So having said that, now we're supposed to explore logistic regression and LDA and naive Bayes and k-nearest neighbors. Okay. And so this is the code for each of those successively. Okay. They all, most of them follow just kind of a very basic pattern here. Okay, so first I'm going to fit the model, whether it's logistic regression or LDA or naive Bayes. The k-nearest neighbors is a little bit different, so we'll get there. But I'm just going to fit it to mcrim, and my formula is regressing or modeling mcrim as a function of, and when I put this period here, it's every other variable in the data set. Okay, so that's that. Notice, so I had to add this little guy right here, this little control argument here, to make the model run. So the way that, well, without getting into the algorithm of how this function works, it goes through several iterations trying to fit the data, and it will only do it to some number. It'll only go through, I don't know what the number is. Call it maybe 30 iterations, and if the model hasn't converged, it stops. And you can say, no, go for longer. Try a max iterations of 100 or something like that. And it will continue to try to fit the model. So I had to do that for this particular one. Okay. But anyway, so I have my fit, and now I'm going to create probabilities. Okay, so of whether my model is predicting above or below the median for the test data. So I'm going to predict. What am I going to predict? I'm going to use the model that I just fit with logit fit, okay? But I'm going to predict not with the training data, but with test data. So that's my new data, okay? And so I go through, and then I'm going to, so that will give me probabilities of being above or below the median. And then I take logit predict, and if the probability found here is above 50%, right? Then I assign it a 1, otherwise a 0. And then I'm going to build a confusion matrix here, okay? And this is what we get. All right. So again, my test error is about 12%, and I'm correctly classifying below 47 times, above 64 times, and then getting it wrong 5 and 10 times, and you can read the table for yourself. Okay. For LDA, it's basically the exact same thing. Okay. So I won't go through the exact same thing that I just did. All right. Naive Bayes, again, basically the same thing, but notice that we don't have a naive Bayes probs here, just because the output of the naive Bayes is just simply the predictions. Okay. Oh well, I guess I might as well run it for you. Okay. So here's naive Bayes. Okay. And then k nearest neighbors. I have k nearest neighbors 10 here, but you can play with this. And again, the k nearest neighbors predict just simply comes out with the classification, so you don't need to go through these intermediate steps of finding the probabilities in the predict. So, all right, but that is it for this one, and then we will be on to chapter 5.